We will discuss we will revise GSC question on topics in one topic. It's a mixture of all subjects. So stay tuned. I will say alright. So in previous video we discussed the different types of distribution problems. So in this we were discussing if objects are discrete. Objects are discrete. And let's say box are. So these type of distribution problems are called unordered distribution. So let's discuss why it is called unordered. What is the logic behind it? We will discuss it. So we can go for ChatGPT. Right. So why? What the hell? Why we were we say a distribution is unordered when district and boxes are identical. So this is saying when objects are distinct and boxes are identical, we classify a distribution. That's why the distribution is unordered because we cannot distribute. So what it is saying guys that when objects are distinct and boxes are identical, so we classify the distribution as unordered because we cannot distinguish between the boxes. This means that two different assignments that is the same object into the same set of boxes are considered to be the same. What's this means that two different assignments that places objects into the same sets of boxes are considered to be the same distribution. Explanation of so what we are saying that each object has a unique identity and meaning that we can differentiate one object from another. This is called distinct object. So we cannot. These are indistinguishable. So swap does not create a new solution. So let's say why they are ordered. If we leave in the boxes, make them distinct, then the arrangement object uh, assume we have objects A, B, C, and D. These are all distinct objects. Alright. We have two boxes. In one box A we put and in another box we put C. So when we put CD in this box and AB in this box, so these both distributions are identical. Alright. Because we cannot distinguish between the boxes. Boxes are same. Distributions are so these both distributions are same. We cannot distinguish between them. So this is how this is another thing. Alright. So we to solve the distribution problem, we have some variations. So one variation comes up is the lower constraint. Lower constraint type, what type of problems it is in the first is type of identical ball in the box problem, which is n minus 1 plus RCR. This formula is limited repetition. Correct. So we have three identical dice are tossed. Let's say. So how many outcomes possible if sum of known all the dice is 5? Correct. So these are no questions here. So this is very tricky question, I say. So let's solve this. So we have identical dice. Identical dice. Correct. How many outcomes if sum of number of dice is 5? Alright. So sum is 5. So what are the only dice possible? 1 to 6. Alright. So here possible sums are 1 to 6, which means and we had sum is equal to 5, which is less than the maximum value we can get from the dice. So we have some boxes. Alright. We have some boxes what? Let's say we have x1, we have box x2, and we have box x2. Right. This is for dice 1, this is for dice 2, this is for dice. Alright. So what this possibly do, this can possibly do. There are three dices which are identical. No. So there is a little bit confusion here, guys. Right. If those dices are identical, so let's say this is one dice, four dice one, this is four dice two, dice three. But these are identical. How can, so let's say this is what? This is a box, X1 box. This is what X2 box. This is what X3. So this box can get value 1 to 6. This is 1 to 6 and 1 to 6. Then these can get values from this. Okay. So all these total values should be 5. So sum is 5. Right? This is the value system. So what we can do, we can remove the lower constraint. We can put 0. So this is greater than 1, all right? Greater than is equal to 1, greater than is equal to 1. So we can get this 0 for all these, sum become 3. So we subtract the sum from this. So 5 minus 3 is equal to 2 here. So what we can do is, this is x1, this is x2, and this greater than 0, greater than equal to 0, greater than equal to 0. And sum we require is now 2. Alright. So what we are saying that this is the sum. Alright. Sum is 2. What is the maximum value of we get it now? Alright? Because we can't get 6 now. It is 0 to 5. But what we can do here, so because why this is, so where we can post that why this is unlimited repetition problem. Why this is unlimited repetition problem. Why not this is limited repetition? Because maximum value we can get. Because we are expecting the sum is 2, which is less than the maximum value. If we were to expect the value, let's say 9. So this problem will become limited repetition problem. Alright, limited repetition problem. If we were to ask you, or we have to solve this with a generating function. Generating function. So now we can do this with n minus 1 plus RCR. This is 4. In this answer we get would be. Okay. So our constraint is subset from the RHS. This is the way to remove the lower constraint. Alright. Now we discuss upper constraints. Right. So what are upper constraints? Upper constraints like to solve direct by n minus 1 plus RCR. So to wait a minute. When we have upper constraints, we need generating functions to solve those type of problems. If we want to solve these problems by n plus 1 plus RCR, this formula. So we have other constraints also on the matrix. So what we can solve directly by this formula. Upper constraints allowed only at one variable. So upper constraints must be on only one variable, and there must not be any lower or upper or any other to use generating constraints. Let's say upper constraint like there are red balls, selected red balls and green balls and blue. Alright? Distribute them and distribute 10 chocolates, right? 10 red chocolates. How many? We have infinite green, infinite these, but only we have less than R is 8, correct? So, what we can do here, guys, this is upper constraint only at one. So, if we have any constraint on other variables, lower or upper, so we can now solve this by this formula. We have generative functions there. So, but here is a special case because we have only one variable which is upper constraint. So, we can solve this by complement method. What is complement method? We can solve this total minus when R is greater than equal to 8 and G is greater than equal to 0 and mu is greater than equal to 0. So this case this case is subtracted from the total one case. Total one case is R is greater than equal to 0, G is greater than equal to 0 and mu is also greater than equal to 0. So this case becomes I can say N is 3 minus 1 plus 10C10 minus what? This case becomes, let's say, R is greater than 8. So if we remove the lower constraint, we have to subtract from. So this becomes R is greater than equal to 0, G is greater than equal to 0, blue is greater than equal to 0, is equal to 2. So 10 minus 8. 10 minus 8, right? So now this will be 3 minus 1 plus 2. So, right. So, was less than equal to less than equal to so 9. So plus 1 C is 1. So this case will become 66 minus 3 is equal to 63. This is the answer. Alright. So now what we will do? First variation of x1 plus x2 plus x2. So let's say first variation of this unlimited differential problem. This is the variation first. We have x1 plus x2 plus x3. These are all unlimited variations of the less than is equal to 10. So how so to solve these type of problems, we need to consider one more variable. Right? Let's say this is all x, right? Which is n. So x1 plus x2 plus x3 is x plus we have some x4, right? Which is 1. So x plus y will be. If when x is 0, right? So y is 10. This will become 10, right? When x is 1, this is 9. When x is 2, this is 8. When x is 3, this is 7. So this is what x, right? This is less than equal to 10. This is less than equal to 10. But what x is equal to 10 is this y variable. This y variable make always this as equal to 10. Right? So this property satisfies this follow satisfy this condition, and this both the conditions satisfy. So this is very useful. Now we have n is equal to 4 and r is equal to 10 already. So 4 minus 1 plus 10c equals 13c10 is 13c3. Alright. So 13c3 is the answer. This is the first variation. Alright. Second variation will be like, let's say, so we have 3 boxes here. 3 boxes. And 10 identical red balls and 15 identical green balls and we have five identical blue balls. So what is the number of ways we can use the identical boxes? So this is a problem of identical box already. So first we distribute 10 red balls into three boxes. Alright? So n is equal to 3 and r is equal to 10. So 3 minus 1 plus 10 is 10. It will become uh, what? 12C2. Similarly, for this, it will become for green balls, it will become 10, 50. No. 15 it will become 72. And for green and for blue balls, it will become 7C2. So total number of ways we can distribute the 12C2 into 17C2 because all those are mutually exclusive events and are independent. So according to all of them, this is the answer. This is multiplication theorem we apply. Combination with limited repetition. So this is a new variation where we use generating function. This is combinations with limited repetition. Alright guys. So this is the new way. In the problems, so for this, remember one generating function equation, which is if we have r to 0 to infinity, n minus 1 plus rcr x2 to power r. This generation function is equivalent to 1 upon what we say 1 minus x to power n. Okay. So remember this generating function and have very smooth journey in these type of things. This is generating function. This is r. This is not a square. This is r only. You know. All right. So we have a question. What question says is question says that we have three identical dice are tossed. How many ways to get some out of outcomes as 12? So we have three identical dice x1, x2, x3. Sum should be 12. Now, what is the maximum value we discussed earlier? Maximum value, but the sum we want to require is 12. So this repetition problem, right? So this cannot get unlimited repetition. If the sum was 5 or 2 or 3 or 4 or 6 or 6 for that matter, so this problem will become unlimited repetition. And we can directly solve by n minus 1 plus RC. This now. Alright. So first we what we say. First we remove the lower constant, which is greater is equal to 1, greater equal to 1. So we do this x1 plus x2 plus x3 is equal to 9. We subtract it and the previous ones. And what we now do is this is now x1 can value get value 5 or x1 xi any x. This is the constant now. Right. I is equal to 3. This is the way. So we have now upper constraint on this. So there is detailed approach and this is a smaller approach. So detailed approach for this problem, x can be one way. X1 power 0, x1 power 2, x1 power 3, x1 power 4. for x on power 5. X1, which was these are identical. X1 can get any value x1 x. So x1 so x1 is square is x1 of x1. So 2 times of x1. So it's 5 times and so on. So how can we solve this is by so n is equal to 5. So we want me n is equal to 6 here. So what do we say here in Right. So by geometry, by QSSE, we can get this as one minus x1 to the power n plus 1, which is upon 1 minus x1. So by geometric distribution, not the geometric distribution, by the geometric series. This is for this only. So for all of them, we can get this expression. So this expression can be got x1 only. This is not about x1 or x2 because those all are identical. Identical, so that's this x is all the values. Two values from this and two values from this are both identical. There is no distinction. So x is the x. 2 is the 2 and the 3. Right. So this will become 1 minus x power 6 upon 1 minus x. This is all of them 1 minus x to power 6 into 1 minus x and 1 minus x to power 6 upon 1 minus x. Alright. These are the things we can get. So to solve this, what we do here 1 minus x to power 6 and 1 minus x to power 6 into 1 minus x to power 6 upon 1 minus x to power 3, which is we all just 1 upon 1 minus x to power n is r is equal to 0 to infinity 1 minus n minus plus rcr x to power r. So here is it will become r is equal to 0 to infinity n is 2 minus 1 plus r is what? RCR x to power r. Alright? So it will become r is equal to 0 to infinity r plus 1 r plus 1 cr. This is 3 r plus 2 will become x to power r. Alright? So what is now we have come across is 1 x to 6 and 1 minus x to power 6. 1 minus x to power 6 is into r is equal to 0 to infinity r plus 2c2 rcr x to power r. So we need sum is 9 here. So we use all the coefficients of x to power 9. So how we can get the coefficient of x to power 9? Or these multiplication. And how we do this? And 1 here we do both of them minus 6 minus x to power 6. This become 12. So we will not include because it is already here 6. Then again do this 1 minus 2 x to power 6 minus x to power 6 and this all will again become this and we what we see when coefficient of x power become greater than n, we does not include because it is not useful. We only need coefficient of x power. You can say 9. So what value of r we put? So it will become x power 9. For this coefficient, we put r is equal to 9 already. So for this, we put 11c9, right? X power 9 plus minus already. 2 into x power 6, we put x power 3. So it will become 5c3 x to power 9 minus this x power 6 already. What will do? This is 3 because so this is 3 of this. So this is the value. Right. So x to power 9 is we take forward what it will become 3 into minus 3 into 5 c2 x to power 9. This is the coefficient, right? 3 into 5 c2. So this it will come across as 25. 25 is the answer. Okay. So now again, we have some more distribution problem. So to solve these type of problems, let's say distribution distribution. So we already know this when order what is the order distribution when we distribute distinct object to distinct box. This is called order distribution. So when it is order distribution, it can be of several types. When order distribution is fully specified. So let's say we have some toys. Okay? So distribute toys. Toys are all distinct into three child. Child are also distinct. So distinct to distinct is order distribution. Order distribution. Right? So when it becomes order distribution, we can specify it also. Let's say first child get three, we can say three toys, and second child gets also three. And rest third child get four toys. Correct. So what we can say to three toys to first child is how many ways? 10 seeds. Correct. Now we have left with 7 toys. So see three ways for this and 4C for this for that side. These are the total number of days we can distribute the toys in order distribution in case of pre-specified days. Alright. But what about the parts if the distribution is partially specified? Let's say we are specifying as first child get at least 3 toys. So only specification we get is first child gets at least 2 toys. This is this is the distribution problem. So this can be get as total distribution minus when uh, first child gets exact no toys, 0 toys, or 1 toys. Right? Total value. So how many ways we can distribute the total? What is the total here? Total here, guys, is every toy has 3 choices. It go to first child, it can go to second child, it can go to three child, third child. So every toy has 3 choices. So 3 to the power 10 is the total number of ways. Right? If this 0 cases, this is manual. 0 cases go. 0 cases when first child does not get any. So every toy has only 2 to the power 10 plus. But when what we say, first child get exactly 1 toy. So to give 10C1 is the ways to distribute the first toy and into how many ways to distribute toys? We can say the rest of the toys to the 2 to power 9.
Alright. So this is 10C1 into 2 power 9 number of ways you can distribute. So this is the number of ways to distribute two toys where first child get at least two toys. Right? So another unordered distribution. So unordered distribution is very interesting here. Unordered distribution is very interesting. So here in unordered distribution, what we see, we divide three boys into three groups, such that each group having exactly one toe. Three toys into three groups. So they are groups. Right? So groups are identical. What we say, identical group to group three. There is no label in the groups. So groups are identical entity. So what we are saying that we have three toys and three groups, right? Three groups. So distribute them in three groups such that each group gets this is today's piece. Each group gets what we say. Each group gets at least one exactly one toe. Which specified means exactly one toe. So three we have to get this one. No, the value for this is 3C1 into 2C1 into 1C1. Alright. These are the this is the distribution problem. But because this is identical, so one and one are repeated three times, right? So what we say, this we will divide with 3 factorial, right? Because one repeats three times. So to when distribution when distribution is identical, right? So we have to divide to distinguish between uh, and two identical distributions. Two identical distribution is because here also one, here also one, here also one. Three times is one is repeating. So these are identical things. So three factorial times we have to distribute divide this. Right? So let's so for simple form it will become three factorial upon one factorial upon one factorial upon one factorial. This is the best case, right? And we have to divide it with three factorial because one repeats three times. Right? So one note here we can we don't neutralize. This is this is for neutralization. No? Neutralization of unordered distribution. Right? Neutralization. So what we are saying here, guys. So we don't utilize distribution order distribution where we have pre-specified distribution. If we have let's say three boys only. So we do not need to utilize the PC1 into 2C1 into 1C1. This is the this order distribution. And also we don't utilize when permutation is limited repetition. Right? So we already know the limited repetition multi-set thing. So right. So let's say we have some questions also here. Let's say there are five people are exactly two and wrong place. So there are five people and exactly two at wrong place. So what does this mean? So we have five people, one, two, three, four, five. So one,
1, 2, 3, 4, 5. So this is person one place, person two place, person three place, person four place, person five.
So what this question is saying, exactly two people at wrong place. So what is this mean?
Two people are wrong place. Are in wrong place. What we can say from this?
Because
Because two people are wrong at wrong place. Exactly three are at right place. So we need to select exactly three people which are at right place. Option three. And to put exactly the rest two people at wrong place. What we can do is because rearrangement of two. Right? So rearrangement we want those people should be at wrong place.
like
So this is correct place. This is wrong place.
and
So we can.
for the rearrangement formula we know r is equal to 2 to n minus 1 to power r fact n upon n factorial upon r factorial.
Right. This is a
Or dn. Dn, alright? This is the formula for dn.
we can solve this. And
So one fusion can arise that
exactly one at wrong place. Is this possible? Let's say this is person one, person two, person two. Person can be again one person can at wrong place. Is this possible? Let's say put P3 and here. P1, P2, and P3. How many people become the at wrong place? One and two. So there is never a possibility where we can say that exactly one
person at it from this.
only
Two or more, right?
so we have pigeonhole principle. We know this is a very
We can
popular topic.
industry scheme that. This is very widely used also.
Pigeonhole principle.
What pigeonhole principle states some keywords also there for pigeonhole principle. We can
One question contain at least how many? These type of questions, keywords. At least how many? Or minimum how many? Right? Base or anything else, etc.
how many ways, at least how many ways.
This is
The
the
type of question we get from the pigeonhole principle. So what it state
that
if n pigeons occupy m holes, alright. So
10 pigeons are there. 10 pigeons. 10 pigeons. 10 alright. And 10 is greater than 1, which means number of pigeons
are more than the number of holes. Holes. So then what it says that at least one hole will have
will have
at least one hole will have at least n1 or n minus 1 by n for plus 1
pigeons. Pigeons.
right. These the
Pigeons.
these number of pigeons
At least one
will contain at least how many pigeons n upon m का ceiling function or
you can say n minus 1 upon n. 4%.
plus 1 right?
So what does we mean about by saying that at least one has two pigeons? Let's say so we are not saying that every hole will have at least one pigeon and then we have to fill. The, let's say we have three pigeon holes and four pigeons. What we can say 4 by 3 same function which is 2. Right? So it will what we are saying that at least one hole, any hole from these, at least one hole will have at least two pigeons. Let's say we have all four pigeons here. Is this satisfying this conclusion? Yes. Let's say we have only two here and one here. Is this satisfying this conclusion? Yes. And let's say we have only one here and two here. Is this satisfying this conclusion? Yes. Let's say we have three here and one here. And here. Is this satisfying this conclusion? So there are several ways to distribute the pigeons in the pigeon holes. But what we as pigeon operators will say, at least one hole will always have two, at least two pigeons. This is not possible that let's say only one, but where we put now other one. So we have to put the other one here or here or here, right? So so one pigeon hole or always have at least two pigeons. This is what this is saying. Let's say if we have identical pigeons and distinct holes, so we have uh, right, we have distinct things. So all right. Thank you so much, guys, for watching the study with us. We will what we say. We'll be back in a few minutes, or we can say 10 or 15 minutes, when we live with you again. We will end the stream here only. Thank you so much for joining the class, or we can say revision class, or we can say co-study class. Right. Thank you so much. We will do that. 7.